Well, thank you. Just want to make sure that everybody can hear me and see me and also see the pointer. Well, you can hear me, but.
Yes, we can hear very well.
Okay, thank you. Okay, so, well, I feel to be a member of this community, but I feel that somehow the mathematics I'm doing is slightly diverging from what you have seen before. There are questions that were here, could be called data, or could be associated to data science. But I tried to find a topic that should be of some interest here. Bandlimited functions. So that was the paradigm of signals to analyze and to process. And this talk is about bandlimited functions and some generalizations. So the origin of all this work is try to understand in a mathematical way what one could do with variable bandwidth. So there's a subfield in signal processing and engineering where this is investigated, and we had our own spin on that. So first I start with history and background. So classical band-limited functions, or Paley-Wiener space in mathematics, consists of all L2 functions whose Fourier transform is supported on an interval negative omega omega. Where? How do I do that?
This is Landaus.
No, that's Linux.
Let's just continue.
Okay. So you hear the echo, and I hear it too. So bandwidth, so the parameter omega is the maximum frequency. That's physical significance. Starting point is the interpretation of Paley-Wiener space as a spectral subspace of some operator. So in our case, that's the second derivative. So operator on L2, and let me recall that the spectral theorem, there are two versions. One version says that there exists a projection value measure. So to every set, you associate an orthogonal projection. The other version is to represent the operator as a multiplication operator. And in this case, the unitary equivalence is given by the Fourier transform, and the second derivative is just multiplication by xi squared. In this version, the spectral projections are just multiplication by a characteristic function, and the spectral values xi squared should be in 0 omega. So the spectral projections are just inverse Fourier transform of this here, characteristic function times Fourier transform. So the insight is the Paley-Wiener space is a spectral subspace, or arises as a spectral projection of the second derivative. Now here is some awkwardness since we take psi squared here, second order derivative. Band-limited functions with bandwidth omega correspond to spectral projection on the interval 0 omega squared. This may confuse you. It has confused me many times, so don't worry. So in higher dimensions, you would look at functions in L2 whose Fourier transform is supported on the ball of radius omega. And again, there's a spectral interpretation. In this case, the underlying operator is Laplacian, negative Laplacian. Its Fourier transform is just multiplication by psi squared. So now, if you take the spectral values in 0 omega, then that corresponds to the spectral subspace associated to the interval 0 omega. And again, the associated Paley-Wiener space can be interpreted as a spectral subspace of the Laplacian. Again, the parameter in the interpretation with the spectral theorem is the largest spectral value. Physical interpretation is largest frequency. So it's again omega on the Paley-Wiener space, omega squared as a spectral subspace. So what are the main problems? The main problems are the eternal problems in this field. Given positions, given data points, can you find a function that gives a functional relation between these? Well, call that data science if you want that. The main point here is that we have an underlying model. I think nowadays you start without the model and try to find the model. But here we have an underlying model. Can we recover? Can we find a functional relation for data? Or can we recover the function in Paley-Wiener space from the samples? Mathematically, that's just encoded into the definition. Sampling set, a set, discrete set lambda in RD is a sampling set for Paley-Wiener space if the discretized L2 norm is equivalent to the L2 norm on this subspace of L2. A dual question is, can we interpolate data? So given a subset lambda, given an arbitrary L2 sequence, we call lambda an interpolating set if we can interpolate arbitrary L2 data on this set. So these are familiar problems. They're rediscovered in every field again and again. I'm in a traditional field, so what's known? And there are the classical theorems of Landau. He proved in a general mathematical context of bandlimited functions in higher dimensions the existence of a threshold between sampling and interpolation. He proved the existence of a critical density. In special cases, that of course goes back to Shannon and the beginning of information theory. So if you have a sampling set, so we assume that a sampling inequality holds on a set lambda, then there is a lower bound on the density of that set. And the precise formulation is that the lower Berling density is bounded below by the volume of the ball of radius omega, and the normalizing factor depends on type of Fourier transform I choose. For interpolating sets, we have an analogous theorem. The upper Berling density must be smaller than or equal to the volume of the ball divided by 2 pi to the d. So this number volume of the ball, is a critical density. You need sufficiently many samples to reconstruct a bandlimited function from its samples, and you need a set sparse enough to interpolate. Now, this set here, this expression here is the Berling density. Roughly, it's the average number of points in a disk of radius r. and they should be uniform over all of RD. There's a minimum distance between points. You can just to be on the safe side. Okay. So this is an insight, and it's a precise mathematical formulation for the threshold between sampling and interpolation. On the practical side, you want sufficient conditions. And in dimension 1, the situation is perfectly satisfactory. Those theorems go back to Berling and Kahan for non-uniform sampling, and I would say almost everything is said by Berling and Kahan. So if the lower Berling density in dimension 1 exceeds omega over pi, and again, uniform separation, then lambda is a sampling set. You have a sampling inequality. And dually, if the upper Berling density is dominated by omega over pi, again, uniform separation, then lambda is interpolating. So the only case that's missing is the precisely critical density. That's been answered too. That's not that easy. But for dimension 1, there's a complete theory to understand sets of sampling and interpolation. In higher dimensions, this is much harder. The density is not an appropriate measure to say something about sampling and interpolation. And so Berling was 1967. It took 50 years to construct sampling sets that are arbitrarily close to the, so they're arbitrarily close to the necessary density condition. These are famous results by Olievsky and Dolanovsky and by Mattei and Meyer. I should say that the remarkable thing is that there's a single set that does it for all sorts of spectra. So they're universal. That's the main discovery. I should add, there are plenty of sufficient conditions with different notions of density, notions that are prevailing in approximation theory, covering density or distance to the next neighbor, whatever. So these are practical, but they're much stronger, require much stronger assumptions. So now let's come to the new part. That's what's motivated by our search for variable bandwidth. Mathematically, all we do is we modify the operator. Instead of second order derivative, we study Sturm-Liouville operator. So between the derivatives, we stick in a multiplication operator. So differentiate, multiply by a function that's bounded away from 0 and bounded, and then differentiate again. I will explain later that this leads to a reasonable concept of variable bandwidth. And in higher dimension, we do the same thing. Instead of looking at Laplace, we again stick in variable symbols, and we have differential operator of order 2, and by imposing conditions on these coefficients, variable coefficients, we replace the Laplacian by uniformly elliptic differential operator. And now comes the first definition. The Paley-Wiener space associated to this differential operator is spectral subspace associated to spectrum 0 omega of this differential operator. There's an innocent variation based on the interpretation of bandlimited functions as spectral subspace and then modifying its underlying operator slightly. Yeah, okay. It should be this here. The decided parameter is the largest spectral value. If you want to compare to bandlimited functions, you need omega squared. But now we are in the realm where we look at spectral subspaces and abstract bandwidth, and then there is no reason to modify the definition just because of the example. So let's start with sufficient conditions. Dimension 1, we have investigated that, and dimension 1, you look at the sampling set, you arrange the sampling points by magnitude, and so here is a definition of uniformly separated. Distance to the next neighbor should be bounded away from 0. So in this case, we have a modified version of the distance. It's modified by this parameterizing function a. And if this distance is less than pi over, okay, here I have a square root of omega, then the sampling set, then we have stable sampling, then we have sampling inequality. So this is an old result of Andreas Klotz and myself. And in dimension 1, this is fairly sharp, provided you use the covering density or distance to the next neighbor. Okay, I should say that this is joint work with Andreas Klotz from Vienna. Old-fashioned collaboration, only 2 people, and it's a genuine collaboration. None of us could have done it without the other. I clearly cannot do that anymore, and he could not do that either. So this is a genuine collaboration, and it's much more than either of us can do alone. So there's also something in higher dimensions, but these results are qualitative. Results are with a covering density, so there exists a radius delta, such that if the balls of radius delta centered at the sampling points cover RD, that case you get a sampling set for this Paley-Wiener space based on the elliptic operator. That's a point. Time to give credit to Isaac Pesenson is, I think, the first one who had the idea to define abstract bandwidth by means of spectral subspaces. So this is a very general concept. Basically, take an unbounded positive operator acting on, say, L2 of RD, or on a Hilbert on an L2 of some set with some measure, and you look at the spectral subspace. And so there are qualitative sampling theorems around. What you need is some kind of smoothness in that Paley-Wiener space, and some estimates on the reproducing kernel. So now the question is, how good are these results? Because yes?
So the operator is, so you start with the function, then you differentiate, you multiply by L-X, differentiate.
Yeah, yes.
So when you differentiate, you multiply by L to the domain, then you multiply by L-X, and then you some law to the domain by three times X, and then you multiply again by.
Okay.
So by on both times more L-X, you can increase the bandwidth. Or it's a no back. So that's why the density is that it would be inversely proportional to the square root of A of X. To the bandwidth of A of X. multiplied by f remains the same bandwidth.
A is a bounded function that's bounded away from 0.
That's all.
Yes.
But so then multiplying by is convolving.
Yes. So convolving with a distribution. Okay.
Right. So but then that will just increase the bandwidth.
Yes.
And then so the bandwidth of H applied to your Wiener signal will be larger than omega.
Well, it will, in general, have infinite bandwidth. There's no comparison.
So then, that's why I find it very surprising that bands only so that we can integrate that here. Because it's not sharply banded. Right? It will be decaying and things like this.
No. Concrete examples. I will try to motivate why this is variable bandwidth. Okay.
So you're sampling an infinite bandwidth signal.
Yes. This comes from a notion of abstract bandwidth, and you're thinking in terms of maximum frequency. We have looked at concrete examples where you take, where the A is a step function. There you can say a bit more. So bandwidth 1 on the negative axis, bandwidth 2 on the positive axis. There you can say something. You basically, similar to splines, where you join together analytic functions at the jumps of the parameterizing function. But I think it doesn't make sense to think of this in such a concrete way. That's what I want to come to at some point. So they're qualitative results, but how good are they? I mean, how large is the delta? If you apply these methods to band-limited functions, you get high oversampling rates, usually. Much too large to be of any use. So one of the fundamental questions is there also something like a critical density in these abstract Paley-Wiener spaces? And if yes, what is the critical density? So first thing is, well, we want to work with Boiling density, lacking any other ideas. The only change is that we may have to look at a different measure. So for now, let's recall the Boiling density with respect to a different measure. It's the number of points in a ball of radius r at x divided by the volume measured in this different, with this different mu. We still take some uniformity over x, and then we take, then we take a limit. So that's the average number of points in balls, but with respect to a different volume. Okay, here comes the main result we proved, answering the question, yes, there exists a critical density, and we can evaluate it. So that's the only theorem that I want to show. So one theorem talk. So we look at the uniformly elliptic differential, partial differential operator of order 2. So here in the form, we stick in variable symbols. Uniform ellipticity means that the matrix of coefficients is positive definite, and the smallest eigenvalue is strictly positive theta, and thus, and the lower bound is independent of the x. Secondly, we assume that these variable coefficients are smooth, So infinitely differentiable, all derivatives bounded. And thirdly, we assume that the coefficients possess slow oscillation. The gradient of the interest goes to 0. Slow oscillation is a fairly general condition. I'll show you an example that this doesn't mean that A itself goes to 0. So you could have so this operator may be far from Laplacian. So these are the three assumptions. Then we define the abstract Paley-Wiener space for this operator to be the spectral subspace for a spectrum between 0 and omega. And we introduce a measure, mu, that's the Lebesgue measure, times the square root, the inverse square root of the determinant of the coefficient matrix. This is equivalent to Lebesgue measure, but it's clearly varying with x. So then we have a version of Landaus theorem. If we have a sampling theorem for this Paley-Wiener space, then the Berling density with respect to this weight is greater than or equal to the volume of the ball of square root omega divided by 2 pi to the d. So here again, you see the difference. The larger spectral value omega leads to the volume of radius square root d. I could write omega squared here, then I have omega here, and it would match with band-limited functions. So the dual result is for interpolation. The upper Berling density cannot exceed this number here, volume of the ball of radius squared of omega over 2 pi to the d. So this looks very innocent. The only change is here. We write a mu. We change the measure. So otherwise, the formulation of the theorem for the necessary density condition is precisely the same. Yeah, okay. The mathematics, however, is quite different. If you look at PDE, constant coefficient PDE is Fourier analysis. You take Fourier transform, look at the Fourier transform and analyze that. When you go to variable coefficient PDE, you have to develop a new theory. And so here, to go from Landaus theorem, density theorem, to this density theorem for Paley-Wiener spaces associated to partial differential operators, we had essentially had to develop a new method how to prove density theorems. So the formulation is the same. Let me say a little bit about the assumptions and the meaning of the theorem. So assumptions 1 and 2, uniform ellipticity and smoothness. We need that to apply results from PDE, basically regularity theory of PDE and some spectral theory of partial differential operators. Now, slow oscillation is something that where a different field enters. But first, let me just point out, in dimension 1, sine of square root x is slowly oscillating. This 1 minus phi is just to remove the singularity at the origin. If you differentiate sine of square root x, then the derivatives will have singularity. So I remove them by setting the function 0 at the origin in a smooth way. So this is slowly oscillating. The function still oscillates between +1 and -1, but slower and slower. Now, the slow oscillation is important in compactness arguments. If we look at the orbit of function or matrix A under translations, so this is a translation shift operator, then this implies that the orbit is compact in C infinity. Also, if we take a sequence xn in Rd that diverges to infinity in any way, and if the limit of the translates converges pointwise, then the convergence is actually in C infinity, and the limit is a constant function. So this is where slow oscillation comes in. Now this is where some of the technical arguments happen. Now let me compare. So again, the classical plane-Wiener space, spectrum of the support of the Fourier transform is in a ball of radius omega. Then Boiling density says that, okay, here we have number of samples in a ball of radius r divided by the volume must exceed this number here. If we remove the limit, or lim inf, from the definition, now we stick in an epsilon. And so this condition means that for every epsilon fixed and r large enough, the number of samples in a ball of radius r is at least 1 minus epsilon times volume of this ball times the volume of the spectrum times volume of this ball. Now, okay, to compare, I choose the spectrum between 0 and omega squared, corresponding spectral subspace. So if you compare here at squared omega, if I take omega squared, I have the right volume of the spectrum. And now now the necessary density condition says in a ball of radius r at x, the number of samples is at least 1 minus epsilon, volume of the spectrum, times the volume of the ball of radius r measured in this with respect to this new measure. So A is slowly oscillating. So roughly what's written here is A of y to the negative 1/2 times the volume of the Euclidean volume of the ball. So this means that near x, I need the number of samples that I need is the same as the number of samples that I would need for a classically bandlimited functions with bandwidth a and determinant ax to the negative 1/2d. Volume scales with power d. And this is why we say variable bandwidth. Okay, if a is constant, then we are back to Landau. But here you see how the sampling density, the required density, depends on the parametrizing function or the coefficients of the differential operator. That's where we come from, and that's how this whole thing evolved. So I have about 10 minutes. One theorem talk requires at least some remarks on the proof. And there are two parts. Well, the proof unites several ingredients. One, an abstract density theorem in reproducing kernel Hilbert spaces. And there are so many density theorems in complex analysis, in signal processing. Whenever you have a signal model, you want to know these basic questions. Is there a necessary density condition? Is there something of a Nyquist rate or not? And at some point it got boring because there are 2 or 3 techniques that you can repeat and modify. So I think the right right setting is start with reproducing kernel Hilbert spaces and ask for density conditions there. So the general setup would be to start with a metric measure space and a reproducing kernel Hilbert space inside the L2 of this metric measure space. Reproducing kernel Hilbert space means point evaluations are continuous. So point evaluation, it comes with a linear functional in that Hilbert space. And this linear functional, when I write it in terms of variables, defines a kernel function that gives you the projection from L2 into this space. So once again, reminder of Borling density with respect to the given measure. And in that case, the question is, what would be the right Nyquist rate? So far, we have already seen it depends on the volume of the spectrum of volume of the Fourier transform, support of the Fourier transform. Now here they define something else. There's an average trace of the reproducing kernel. So you take the diagonal of the reproducing kernel, take its average over balls in this metric space. And then you repeat, take the infimum, so I have some uniformity over the space X, and then you take lim inf, same with lim sup, upper Borling density. And what we proved some years ago was that under a certain natural hypothesis, which I'll mention in the next slide, there is as an analogous theorem to Landaus. If you have a set of sampling in this reproducing kernel Hilbert space, so if you have sampling inequality for all functions in the reproducing kernel Hilbert space, then the lower Borling density with respect to the measure must exceed this average trace, the lower trace. And for interpolating, you replace lower by upper densities. In a way, that's a pleasant result. It implies Landaus density conditions, implies the density theorems for Gabor frames, for density conditions in complex analysis in Fock space, density conditions, or new density conditions for in Corbett theory. So this is a fairly general theorem. And unless you are critical and ask about wavelets, this is general enough. But of course, there's lots and lots of reproducing kernel Hilbert spaces excluded, to which this theorem does not apply. The insight was, this is the quantity. The average trace of the reproducing kernel gives you the threshold between sampling and interpolation. Now, what is natural in this theorem? Well, there are some assumptions on the metric and the measure, some compatibility between the metric and the measure, doubling measure, non-degenerate balls, but I don't have to deal with that because in the case of differential operators, we use a measure that's equivalent to Lebesgue measure. So the decisive conditions are conditions on the kernel. The diagonal of the reproducing kernel should be bounded away from 0 and infinity. It should be bounded. The kernel should have some off-diagonal decay. It's expressed in this way here, weak localization. So this, well, if we think of the reproducing kernel at X, where we evaluate, the support of the reproducing kernel should be near X. And as X varies, the support should always have the same size, and this is what expressed this way. So the supports on the reproducing kernel are essentially near the point where we evaluate. So that's the technical condition. And there's a similar condition when we on the sampling set, so where we sample, so that there's a discrete condition as well. The many limbs and soups, integral and sum don't matter. So there are two conditions that signify some weak form of off-diagonal decay. So now let's go back to spectral subspace of differential operator. You can show that the spectral subspaces are reproducing kernel Hilbert spaces. By regularity theory, they are embedded in all subular spaces, so that's fine. And now we want to apply that abstract theorem. So all you need to do is to check these three conditions on the reproducing kernel. So our first way was to ask some experts in PDE, notably Wilhelm Schlag. They all say, yes, there should be something we don't know. And I think the reproducing kernel of these spectral subspaces, that's a natural object that should be of interest in PDE. It seems that there's not too much known. I cannot tell for sure. So we had to come up with something and learned quite a bit of spectral theory. So we want to verify these conditions, weak localization, and so on, for the reproducing kernel in these spectral subspaces. And the main insight in this analysis was that the reproducing kernel of the spectral subspace depends in some way continuously on the symbol, on these coefficients. Clear. So we assume that the coefficients of the differential operator are smooth, slowly varying, and then we look at translates of the coefficients. We take a diverging sequence of points xn and assume that the shifts converge pointwise. Oh, there should be an x. Then the reproducing kernel and this Paley-Wiener space centered at the origin converges to the reproducing kernel of the limit function at the origin. So the secret is to take the reproducing kernels, center them, move them back to the origin, and compare them. Should I continue or just stop? Well, okay. So let's see. So underlying is that we were searching for some kind of translation invariance. So there's some kind of asymptotic translation invariance. Conjugate the operator with translation. So what happens? Here is the operator, here are the translations. We pull in, there's still a y here, okay? So we pull in the translation, okay? We get this here, and otherwise it's nothing changed. So conjugation amounts to shifting the coefficients of the differential operator. Now, then, as we noticed, or as I indicated, if the orbit of the shifts of the coefficient is compact, then we can show that then this implies that the orbit of the operator applied to f is also compact. Keyword is limit operators. That's a technique in spectral theory.
So I guess he differentiated spectral variables in y.
Yes, this is a misprint here. Here the y is correct.
You have the symbol EDX statement. How it should be done.
Well, all I did is I commute the translation through the first differential operator.
Yeah, for the,
This should be this should be a y.
yeah. But then the differentiation is
With respect to
x over
with respect to y. Okay. So one slide. So one of the insights, morally, the reproducing kernel is just a spectral projection applied to the point measure. It's probably something, if you work with reproducing kernel Hilbert spaces, you have observed that too. So morally, I say, so what you do is you approximate the point measure with a smooth, with an approximate identity and work with this. And then what you do is the following. So here's the centered reproducing kernel. So we write the reproducing kernel as spectral projection applied to the point measure at xn. Here we have the conjugation of the operator by translation. So that, of course, with spectral calculus go through, it's a spectral projection of the operator with shifted symbol applied to point measure. And here comes in all the spectral theory of unbounded self-adjoint operators and how the spectrum depends on perturbation and so on. The symbol coefficients converge to B, and therefore the spectral projections converge. So there's a lot of spectral theory involved, but this is all, you can find the right book and learn it. And this here is the reproducing kernel of the operator with symbol B. Now, as I mentioned, slow oscillation means that every limit point is a constant function. So here we deal with a constant coefficient differential operator for which we know how the formulas look like. So maybe it's confusing, but I want to point out there are several ideas going in reproducing kernel Hilbert spaces, regularity theory of PDE, spectral theory of unbounded self-adjoint operators. We used, and in the background is a compactification. The word is Hickson compactification. Point is, it's not metrizable. So at some point we have even go to nets instead of sequences. So aesthetically, that's, I would say, pleasing, but too much for a pre-launch talk. I think there are ideas that should be able to use elsewhere. My favorite question would be, is there anything one could do with graphs and the graph Laplacian? Because I think nobody knows whether or not there exists a critical density for Cayley-Wiener spaces with respect to graph Laplacian. And many of the elements are in place, but there's still lots of work to do. Okay, then thank you. And let's have lunch.